when I will talk about the joint work with Peng Shan and Wen Binyan, they're colleagues at Tsinghua. And so, and all the motivation from the physics parts, I learned it from them. I have to admit, like, speaking about this still like speaking a foreign language for me. So please forgive me if I say something wrong. So we have heard this 4D 2D duality from Tom's talk. So we have 4D n equals to q superconformal field theory. So some physicists, they have associated a vertex algebra. And so it's called, so if you have a theory here and call this vertex algebra V of t, and we have learned that the Higgs branch of this theory is supposed to be the associated variety of this vertex algebra.
There's no S in beam.
Thank you. And then, so we'll be interested in a family of 4D theory, which comes from like reduction from a 6D theory. So it's a 62,0 SCFT, which is compactified on a Riemann surface. So C will be a Riemann surface for me. So if you look at 4D theory coming from here, then there's a description for their Coulomb branch. Which is given by some moduli space of Higgs bundles on this Riemann surface C. So this is the data of a G bundle. So underlying there is some group G, gauge group G, hanging around, and so this is like an epsilon is a G bundle on C, and then phi is a Higgs field with some particular conditions. And then so we are yet interested in a very special case, which physicists call generalized Algebras-Douglas theory. And here, the Riemann surface here is just a sphere, but with two punctures. So, so it's S2, and then you have two punctures. And the corresponding Higgs as our Coulomb branch we're going to consider. So we will we require this Higgs field have some regular singularity at one of, let's call them 0 and infinity. So phi has regular singularity at 0, and then and then it has some irregular singularity at infinity. And it turns out this case, what appears, the vertex algebra appeared on the other side, is a representation of W-algebras at some level, like boundary admissible level or some non-admissible level. Well, here's some W-algebra appearing. So let me just be a bit vague for the moment. And then, so this is the setting we'll be discussing in this talk. And so, so recently there have been lots of study in math literatures for like 3D n equals to 4 what's this? It's like this. I don't remember. Ben, correct me. Yes. So this is and it's in mathematics. So we talk. Yeah, I don't know. I think there's motivation from physics. There's this symplectic duality. And it is formulated as follows. So if you reduce a 6D theory to 3D, then you still have Coulomb branch and Higgs branch. And then in that setting, you can, so say on one side, if you have geometry, like you have a symplectic resolution, and then you can consider a category O associated to this symplectic resolution. So this is a category of sheaves. So it's a geometric version of sheaves on this X. And then it has a, so in some cases it has a dual resolution. And the Coulomb branch of this theory is supposed to be the variety here. And so if you and it's expected there's this causal duality between this side and so here was O for this X trick, but this category you can obtain from O of quantization of this variety. Means you obtain from a quantization of the other branch. So. So it's an O of, let me just put, where should I put it? Like the O for an algebra A which quantize this Y. And so what we sort of propose is something, so this is like this, for example, this conjecture, many examples of this kind in work by Braden, Mikata, Profut, and Webster. And so we sort of want to study such an analog in 4D. And in 4D, on the Coulomb side, you always have a geometric space. That means you want to study category of sheaves on this Hitchin moduli space. But you don't always have a variety on the other side. But on the contrary, you always have this quantization, which is supposed to be replaced by representation of this vertex algebra. So somehow the proposal is that there should be some sort of whatever causal type duality between sheaves on the Coulomb branch and representation of this of the corresponding vertex algebra. Maybe I just put W. Okay. And what I'm going to explain today is just sort of a very how do I say, primitive, some sort of hints of why this kind of things will be true, and it's only at the numerical level at the moment. So what I'm going to speak is to talk about it's a bijection between some C star fixed point in this variety and irreducible representations for the W-algebra on this side. And then I will discuss about, for the irreducible representation of W-algebra, you have modularity, you have this SL2Z action on the characters, and I will try to explain how a way to interpret that on the fiber side using double affine Haiku algebras. And yeah, and so that's basically the plan. Any questions?
What type of W-algebra representations are you talking about? What is that?
I will be more precise later. So I will first start with with admissible representations. So this has been appeared already several times in this talk, in this conference. So So that means yeah. So let's fix G hat to be affine Lie algebra. So yeah, in theory I can take any affine Lie algebra, but just to simplify this talk, I will take affine Lie algebra associated with a simply laced finite Lie algebra. So it's a G simply laced. Then affine Lie algebra with usual notation, and then I'll fix a carton. And then, so we've seen in the talk this morning that so a level kappa is like principal admissible. I will only consider a principal case. It has the following form. So if kappa plus the dual Coxeter number is equal to P over U, where PU are co-prime positive integers, and P is bigger or equal to the dual Coxeter number. And I will only consider the boundary case. So I will stop saying principal for now. I only consider principal case. That is, I fix kappa to be of this form. So I take P equals to H over U, where U is an integer co-prime to H.
So a stupid question. I thought the difference between principal and co-principal was something between co-prime to the lacing.
Yeah. So if I do this assumption, yeah, it doesn't. No. So yeah, maybe I should say for all intents and purposes, no, unless I specialize. Otherwise, it will work for any affine Lie algebra.
Okay, yeah.
Just to simplify my notation, I will do this case. So yeah, so that's why I always have this thing in mind. I should.
And these are exactly the levels that appear in Archimedes. These are exactly the levels that physics needs.
Yeah. So this is somehow this is the among the admissible ones. This is the only one which appear here, but there's also some non-admissible ones which are interesting with here as well. But, yeah. But for the moment, let's do this. And then await lambda of level kappa is principal admissible if it satisfies the following conditions. So if lambda is a regular dominant weight, so i.e. If lambda plus the shift by rho pair with any positive co-roots doesn't belongs to 0, -1, like negative integer. And also you require the integral co-root system for lambda is isomorphic to the initial co-root system. So we have seen this already. And so I will denote by admi kappa the set of all principal admissible weight of level kappa. And so this set, well, this notion was introduced by Kaiser and Matsumoto, and yeah. And so they studied these sets, and now we know how it is parametrized. So in the boundary case, the parametrization is it's a bit simpler. So you just consider the dot action of the extended affine Weil group on the element kappa times lambda 0. And then, so here, W is an element in the extended affine Weil group, which is W semi-direct product with the co-weight lattice. And then you need to put a condition here to so all these elements satisfy this condition. But you need to put the condition to make sure that your element stays regular dominant. So that condition is that it sends this set of co-roots to positive co-roots, affine co-roots. So so here pi u is the set of, so you have all the finite simple co-roots, and then you have this minus theta type. So the u appears here. Right, and then so there's a, so this is just a description of the elements in this set, but it's not a parametrization because you may have different w's which give you the same weight, and then by work of Katz-Frankel and Wakimoto, you actually get a parametrization of this set in terms of the following things. You take your co-weight lattice modulo u times your co-root lattice, and then you can quotient the entire thing by this outer automorphism group omega. So omega identifies with u times p check over u times q check. So it just acts by multiplication on this. So so there's a bijection between this set with the set of admissible weights of level kappa. Well, this actually can be made very precise, but I don't want to go into the details. So basically, what you can do is you can identify the upper set here as a subset inside inside the extended affine Weil group. So let me denote. Yeah, okay. So I will denote by yeah, maybe let me put this. So I will. So there's a particular subset. Let me denote by sigma u, which consists of elements just determined by a translation, an element in p check. So for any element in p check, you have translation by it, and then you can always write it as pi b times some element ub in the finite Weil group, which sends your b to an anti-dominant weight, and with some extra condition, this determines ub uniquely. So for any b element, pi b like this, and you can choose a particular, you can describe a particular subset of this pi b by putting conditions on b such that they represent this set here. So yeah, so this is already in this work. I just say it in a different way because I use it later on like this. So in other words, if I I will put a bijection between sigma u and I should really do sigma u quotient omega. Well, like sigma u to be that quotient, and I do a bijection with this, such that for any b, so for any pi b here, so this is considered to be an element in the extended affine Weil group, and the corresponding element will be pi b dot action on k on kappa lambda 0. Okay. Okay. Anyway, so this is some calculation for something I will talk about later. So anyway, you get the parametrization of this set, and then so the vertex algebra will be worked. Well, I guess you all know now. That so we're considering so that V kappa be this universal vertex algebra given by induction of the one-dimensional representation of level kappa, and then we have this simple quotient, and kappa is in this boundary admissible level. We have this simple quotient. Of VK as a representation, also as a vertex algebra, and so the irreducible representation of this thing is the admissible representations. So this is like L lambda or lambda in this admissible kappa.
They're not all reducible, they're all
In the category.
highest weight reducible.
Highest weight irreducible. Yeah, should say irreducible in category O. Yeah, and then Tomoyuki proved that this vertex algebra is rational in category O, meaning that this representation in category O is semi-simple. So you basically have all the simple objects here. And now we want to do something like this. With here, it's LK, L kappa, and then so it has to, that we want to match it with some C star fixed points in the Hitchin system. But there we actually will use a local model for the Hitchin system involved, and so we replace our Hitchin system by a so-called elliptic affine Springer fiber. So for this, I take G check to be the long-length dual Lie algebra. And then I take H check. And also, so this is the Cartan due to the data fixed at the beginning. And also, since I fixed the positive roots, so here I'll also I'll talk about this later. So this is a Cartan. And then, so let capital G check be the corresponding algebra. So it's like connected complex algebraic group. I would take the adjoint type, and so whose Lie algebra is G check. And then I'll consider its loop group. So so let K be the field of Goron power series, and then inside I have the ring of integers. And then we can consider like the in group G hat of K, and then consider G hat of G check of O as a maximal parahoric subgroup. We'll need a sort of like affine flag variety. So to define that, you will need to consider the Iwahara subgroup. So for elements in O, you can evaluate Z to 0. So you have a group homomorphism from here to G check by putting Z to 0. And then, so here we have a Borel corresponding to the choice of positive root system on the other side. And I take its pre-image under this evaluation map, and this will be the Iwahara subgroup. So this is EV inverse D check. And then the affine flag variety is the in scheme, and whose close points is parametrized by the coset of I check inside this loop group. And so I'm taking a Springer fiber, which will be closed in subscheme here. But for that, I will choose an element gamma. So that gamma. So gamma will be an element which lives in the Lie algebra. In this Lie algebra, and it is given as follows. So I take before my co-roots. My co-roots here will be a root for G check, and I take the corresponding root vectors. So I do sum of I equals to 1 LE alpha I check, and plus the root vector corresponding to this guy, this minus theta check plus UK. So that is an F theta check times Z to the power of U. So and then the affine Springer fiber is so whose point it consists of following elements. So it's a sub scheme inside the flag. So its points are cosets of the Uehari, and I ask this element satisfy the following condition. So it's like G inverse times gamma G belongs to the Lie algebra of the Uehari. So what this condition means is, like, if you think of this element as a vector field on the flag manifold, this is the fixed point of that vector field. And so this particular element of this form is a so-called elliptic element. So this is a terminology I get you to touch the linguistic. And so these varieties were first defined and studied by them. And in this case, this is a finite dimensional projective variety. Now, moreover, so on our our flag variety is a quotient like this. So you have an action of G check K by multiplication on the left. Okay. And so you can take take T check K inside here, but then here you not only have like G check K action, but you also have a so-called loop rotation C star action. So the action of that element T in the C star, it just rotates your variable Z. Just multiply your variable Z. That's like a loop rotation. And so we have this thing acting on the affine flag variety, but it has no reason to stabilize the fiber. What will act on the fiber is actually a one parameter subgroup inside here, which is given by sending T to the following element. So you think of rho on that side as a co-character for T check. And so you have T to the power of rho. And then here you do T H check. There's a U somewhere.
And this T capital is a subgroup of translations in the while group. This T hat, T check or whatever.
Yes, this is like translation well, it's more like, yeah, it's quotient by T check of O is the translation in well. So yeah, so I'm missing the U here. And you can check that this, if you consider this element acts by a joint action on the Lie algebra, it just dilates this element gamma. So this is like a homogeneous element. And therefore, this C star will continue to act on this Springer fiber. So you have, so I fix this C star. From now on, like whenever I talk about C star, will be this subgroup. And this, you get from here a C star action on on this fiber.
Sorry, what is the power on the first t? Is it u times
U
b?
times rho. So
Oh,
rho.
Okay.
Yeah.
Got it.
So
It is t to the power u rho. It is
U, yeah, rho.
p is rho. Okay.
And then, so you can consider the fixed point. This set is actually the C star fixed point. Well, you can show it's actually contained in the T-check fixed point of the entire flag variety, and this is the extended affine group. And so I can parameterize these fixed points as a subset here. And this subset, if you look at it, when it's a fixed point, when does it satisfy this condition? It's precisely when it satisfies this condition here. So yeah, so under this identification, gamma C star is the element, is W in X. Oh, actually W inverse. So it's like W inverse sends high U check to positive roots. Positive. So now all these are roots for in this geometric setting. And then you have this omega action hanging around because I took I took my group to be of a joint type, and actually in this case the flag variety is not connected, and its component group is this omega. And then inside each component, the elliptic fiber is connected. So you also have an action of omega on the fiber, and therefore you have an action of omega on this set. Okay. So so then you can identify.
I'm sorry, can you explain again? Okay, you start with the C star fixed point, this one trigger fiber. How do you, that inclusion you wrote there, can you explain that again?
This.
Yeah.
Oh, this is just essentially because gamma is a regular semi-simple element. No, it's like rho. It's no. Let me say it again. So it's like the rho fixed points is the same as the T fixed points. Like rho is a regular character.
Okay, yeah.
Yeah. So yeah, and so if you modulo this component group action is the same as taking fixed point in just one single in the neutral component of gamma. So if you want, you can also identify this with the fiber of the simply connected group, but it's less natural. And then so there's something to deal with about how do you do this quotient, etc. But I think you get the idea. So the first theorem we've shown is that you have a natural bijection between this C star fixed point in this fiber and the irreducible representations inside the category O of L kappa. And it's just given by sending an element. So an element here will be a W, just send it to W inverse dot action on kappa of lambda 0.
Your definition of gamma is that U's assumed to be positive.
U is always positive,
Yeah.
yes. Okay, and yeah, so I want to make a remark here that all I said till now works for any affine algebra. So, but you need to do the correct analog on the other side. So, so this works for any, if you take just miscible representations for affine Lie algebra G, as you call it G hat, but it can even be twisted type. And then on the other side, you will consider a fixed point in the Springer fiber for the long length dual of your affine Lie algebra. So for example, if here you have a non-simply laced but non-twisted affine Lie algebra, you will get twisted affine Lie algebra on this side. And actually, in physics, they're only interested in those cases. Like, they won't consider twisted affine Lie algebra here.
Is kappa still principal admissible, or can it be?
Kappa is boundary admissible.
Sorry, boundary
Yes.
admissible. Yes.
Okay. Any questions? Okay, if not, let me proceed to modularity. So on representation side, again, this was studied by Kaz and Makimoto.
I do have a question. So, like, there was some, like, Fredrickson and Knightsky had a similar.
Oh yeah, thank you. I forgot to talk about that. Yeah, I'm sorry. So yeah, Fredrickson. So like a first example where this was noticed was by. Now I need to spell the name correct. I have it in my notes. Let me get it correct.
I think the first I should be an E, and then the second E shouldn't be there.
I'm impressed by your ability of spelling names.
Well, that's the name of my neighborhood, Frederick.
And nice. So they first, in 2017, so they first observed that there is such a bijection for W and M. And then there's some work also by Fredrickson and Hay and yeah, in some other examples, basically SL2 hat and then WNBN. So some other examples, but this is like uniform for any.
And so, I mean, I guess the question was something like, is there some compatibility where it's like Drinfeld Sokolov reduction and the one?
We'll talk about that later. It's the third part of the talk. Hope I will get there. So.
What is the BN?
I don't know. It's not a question for me.
These are certain subregular W-algebras.
Okay, so for any lambda admissible, so we have this representation L lambda, and we can consider its character. So this is like notation for characters of L lambda, which we have already seen. So you consider it as it's more like renormalized character. So you take the trace. So yeah, so this is a function on y, where y is the following subset in H check, consisting of elements of the following form. So you have z tau and yeah, I should write it like 2 pi I times z plus e times k and minus tau times b. So inside H hat, and then you require tau belongs to the upper half plane. So Z is an element in the finite carton, and Yeah, and t is a complex number. And so this is just its value at an element v in y is given by the trace of e to the power of v on L lambda, and then there's some renormalization factor. Right. So these characters, they are linearly independent in this space, and on this space you can define an SL2Z action.
Sorry, Peng, can I just
Yeah.
make a point?
Sure.
So, in the definition of y, you can't take z to be in all range. You can only take z to be in certain strips.
Yeah, it's very important.
It's important.
So, what would be
These characters do not converge for all values. There are holes in z.
but can I just if I don't talk about holomorphic functions, I just talk about meromorphic functions.
Well, you're just saying functions on y, so I wanted to make the point that this is not a function on y. It's a function on a strip, which is a subset of y.
Oh, okay.
We can talk about it later.
Yeah, I would appreciate that. Sorry, yeah.
But it is incredibly important.
Thanks. Yeah. So but yeah, so like, if I restrict to that part, then I have a SL2Z action.
There is no SL2Z action on this space. You have to meromorphically continue, but then you lose the factor of the character. Again, we can talk about this later.
Okay, maybe I should just say that I will consider a vector space which has a basis spanned by the characters, and for lambda admissible, and then it has an SL2Z action with the SNT matrix given just in the paper of Katz and Wakimoto.
Because you see, weight spaces can be infinite dimensional
Yes.
for admissible representations. That's why there could be divergences. But you get meromorphic functions anyway.
Yes.
Okay, so it acts on the space of meromorphic functions.
Yes. That's what. Yeah.
Yeah, we'll talk about it later, because this is important. This is why the Valenda formula fails.
I agree completely. Wherein the formula fails.
Yeah.
Yes. But I just need a space where it has an SL2Z action.
Yeah.
And I have explicit coefficients for that SL2Z, for that ST matrix.
So you can meromorphically extend and that will
Yeah.
work.
Yeah.
But they're no longer the characters.
I agree. Right. Yeah. Like I don't discuss any like within the. Like there's no like modular tensor calculus. But I consider this vector space with this SL2Z action, and there are explicit formulas for how an S and T matrix acts on these elements, on these functions here. And then now so now I want to explain this by another context, which is coming from so-called double affine algebras. And I hope I can in time, but I really want to explain this. So so I will not explain you the definition of Daha. So this is a two-parameter associative non-commutative algebra, and it's so this Q and T are parameters deforming the range of functions. So you have two copies of polynomial functions. So one is indexed by by x. So here it's like it has basis given by xb, and it multiplies as you imagine. So it's like functions on t, and then yeah, maybe I should just write, you know, like functions on t cross t du semi-direct product with w. And then so here I will denote like functions in one copy of t by x, so and the other by y. So we have two polynomial subalgebras here, and then it has a remarkable representation, which is it's a polynomial representation. So I use the x variables, and it has a basis. So this is a kind of a renormalized non-symmetric Macdonald polynomial. And they're characterized, so it forms a linear basis of this polynomial representation. And it has the property that they're eigenvectors for the y operator's action. So they're eigenvectors for functions in y. Okay, and then so I will specialize to the case where, so if I want to consider the case relevant to this fiber, I will explain you later where the fiber shows up, but so first of all, I specialize my parameter to the following situation. So I take t to the power of h check is q to the power of minus u, where for now I assume q to be a generic number, complex number. And then, so in this case, after this specialization, so I just write my Daha depending on this u. Acting on this polynomial representation, it has a unique finite dimensional quotient. So it has a unique finite dimensional quotient. So I will denote it by V Daha. And so this quotient have different descriptions, but you can, so this was like actually first studied by Cherenik. And so what happens here is that under this quotient map, your Macdonald polynomial, it either goes to a basis vector or it goes to 0 if and only if, so B does not belong to that set sigma u I defined before. Okay. And therefore, those who belongs to sigma u form a basis of this quotient. And moreover, the action of x is also semi-simple. Of this part is semi-simple on this representation, because you have a, so like, yeah, I should say the other things specialize while, and they give a eigenbasis for your x action. So your x action is also semi-simple. And so this is a remarkable, and so therefore you can just identify, so since x action is semi-simple, so then this representation is nothing but just functions on this finite set. Okay, and now so for this representation, so Cherenik introduced some central extension of ESL2C as some sort of projective automorphisms of Daha. And then you also have an action of this this group as a projective automorphism of this representation in a way that it is compatible with the action. And so let me tell you what is the S matrix action here. So the S matrix action is given by some sort of Fourier transform where just it sends a function f to the following function. So its value on an element, so it's a function here, and so its value on an element pi of b belongs to sigma u is just given by you do integral. Well, there's some measure on this function on this set, which let me not explain. So it's just you do the product of your Macdonald polynomial with f, and then integrate. So basically, if you take under this map, if you take so yeah, just using this, you can compute how your basis is. Okay, maybe. Sorry, let me say things in their correct order. So my space is function on this set sigma u, and in particular I have a basis just given by characteristic functions at each of the points. So let me just write chi x for x sigma u, and here chi x is the function. This is delta xy for x and y sigma u. And then you can compute the S matrix in this basis. And so if you have an S, let's say pi b and pi b prime, and so it's like matrix coefficient, and these 2 points will just be the evaluation of this renormalized Macdonald polynomial at q to well, some weight which is explicitly determined by b prime. Let me not go into detail, and then times mu times the same thing. So I just want to make the point. So this coefficient is something you compute explicitly using this renormalized Macdonald polynomials, and then
So can you just tell us whatever this measure is? Does it give an individual point like 1 over an integer, or is it something weirder?
You have to remove one prime because you have prime in both places.
no, I have b here, and then I have b
Okay.
primes here. Yes. So this is like I'm evaluating s on f, which is chi b prime, and I look its value at pi b, and it's something like this. I'll answer later about the measure question. So yeah, so the second theorem we show is that
So this is the first theorem.
the first theorem was the bijection between the fixed point.
Ah.
Yeah. So if I set q to be the following roots of unity, so exponential of minus 2 pi I h check over u, then in this case, with my condition over there, actually t is equal to 1. And then, so you see we have two vector spaces. So first that one, let me call that one V of characters. So this has a basis indexed by characters, and the other is this V of V, let's say Daha. And then if I have So if I will send this characteristic function on this side for an element in sigma u to the corresponding character. So remember, yeah, like the corresponding character here is actually like x inverse dot, or no, rather x dot kappa lambda 0. Okay. So the bijection in the first theorem give me isomorphism of vector spaces, and now the state and here, yeah, I need to modify by some sign which is related to the finite one group part of this element. Let me, yeah, not give the definition, but you need to. So there's some sign appearing here, and then this isomorphism is compatible with SL2Z action. So this is what I mean by maybe modularity is not a good name, but this is what I mean. Like you can interpret the ST matrix for the characters via this language of Daha, and the relation with the fiber is the following. So. So there is a geometric realization of Daha due to A plus whole. So this can be realized as K-theory of some equivalent K-theory of affine Sternberg variety with a product given by some convolution product. And in this picture, it will act naturally on, like if you specialize this to copy of C star is to this to that T check magnitude Q minus U, then this acts on the C star equivalent K theory of our Springer fiber.
It's Q to what power minus?
H check equals Q T to
U. Okay. Q to the minus U.
yeah, minus U. And so, so this, if you localize, meaning you invert this Q parameter, this is the same as the K theory of the fixed point. And since the fixed points are isolated, this K theory just function on this finite set. And this is the geometric realization of that module I was telling you over there. Okay, so W-algebras.
What is ST hat?
It's a fine version of Sternberg variety. So can I go over a little bit?
Can I ask a question?
Yes. then there will be no W.
Ask you a question.
In these physics papers, they also computed this S, but they had it as depending on T, what they call T, and only under specialization they recovered the S matrix of the affine BOA, and now you also specialize. So
Yes.
could it be that if you don't specialize, you exactly recover what the physicists said?
Which
Yeah, the second paper.
Oh yeah, so they
You see, they had this S depending on T.
no, maybe let's talk about this later. There is, yeah,
And then they notice if they specialize similar to how you did in Theorem 2, that they recover the S matrix from the affine BOA as expected.
so what is the T?
I forgot.
Yeah, so maybe let's talk about it. But this is a good point. I want also to make it so. So it's like this thing is defined for any generic Q. So this like SL2Z module, it exists for Q without, which is not roots of unity. But that condition is crucial.
Yeah.
Yeah. but it's only when Q is roots of unity it coincides with this. Yes. So, well, I don't know if there's a theory of vertex algebra for Q generic. That would be interesting.
I mean, there are various options to explain these deformations, but
yeah, let's talk about it later. That would be super. So W-algebras.
How much time do you need?
Wow.
Can you give us a
Yeah, I would try.
punchy-
I would try in 5 minutes. Let's see. Hopefully.
Stop you at 5 minutes.
I can also stop here.
We put it to the vote?
Let's do that.
Yeah, 5 more minutes.
Please.
2 minutes. Yeah.
So
I set a timer.
so to simplify my life, I fix F a nilpotent element in G. So in finite G, and then I would suppose it has a good even grading. Just to simplify my life, even grading. And what is important is that I will need to assume that F is regular in a Levy. In a Levy of G. So this is an important assumption for me. And then I consider this W-algebra, which is obtained from this positive quantum Drinfeld reduction, Drinfeld-Sokolov reduction of this LK of this simple vertex algebra we discussed earlier, and then as we have seen in Gerbier's talk, you have also a minus reduction, which give you a functor from modulus over LK to modulus over. Let me simplify my notation. Just write it as WK. And then there's some conjecture, and in some cases it's a theorem about how this functor behaves on simple modulus. So there was initially this conjecture by Katz-Run and Wakimoto, which was more about the universal W-algebra, and then I allowed the permission to put the name here before I talk. Which says that if now for lambda admissible, if you do the reduction of a simple module, so for lambda, first the statement, it is simple if it is not 0. And then the next statement tells you when it is a criterion for when it is not 0. If so this is if and only if. So let's see. So we know that our lambda is x dot of kappa lambda 0, and this happens if x sends this at pi u to phi tag, but you remove the roots root system of your Levy. Okay. And then finally, there are cases where you can have simple modules whose image coincide. This happens if and only if lambda and lambda prime belongs to the same orbit for the Y group of your Levy. And now, so I want to explain. So, and conjecturally, you obtain all your irreducible representations for W like this, and this is
And what's WL?
this is the this is
Levy. Ah, okay.
yeah the well group for the Levy. and so
Are you able to jump ahead to the punchline?
Right. So okay. So this is true for type for principal nilpotent and also all nilpotent in type A and this exceptional type.
It is not boundary level in this.
It's boundary.
In
So
this
I.
theorem. In this.
Oh, this is maybe more general. This is like admissible.
Yeah, this is just arbitrary admissible.
Yes.
But these are modules in what category?
Which module?
I mean, the conjecture is concerned about what modules in modules in which category of the W-algebra? Because we will have a similar problem with the as before with the category O. So just I mean, okay.
So I only consider simples obtained in this way. And then the statement, yeah, let me just give the statement and then we'll stop. So, so the statement is that you pick your, so your Levy have a root system, you consider a dual Levy determined by the corresponding co-root system in your G-check. And then you take a parabolic subalgebra here with this Levy factor. And then, so remember we have this GK, GO, and I have this evaluation map to G-check. I will just take the pre-image of this P-check, and then I will consider a partial flag variety G-check K over P-check, and then so this is a partial flag variety. And then I consider a so-called Spitational variety related to this gamma. It's just the elements here. But now instead of requiring G inverse gamma belongs to the Lie algebra of Iwahari, I ask them to belong to the radical of the Lie algebra of this parahoric. And what happens is that this is smaller than the radical of the Iwahari, and you will see that those G's you don't get in here are precisely those you remove from this condition. And then this is a bigger quotient, so this receives a map from the flag variety, and those whose image coincides under this map are precisely those they reduce to the same module. And so yeah, I just want to make the point that this bijection is compatible with this reduction procedure. So you get a C star fixed point bijection with like irreducible representations for W-algebras coming from this procedure. And yeah, and you can compute the number of this set. There's an explicit formula, and you can show that the SL2Z action is also compatible, etc. Okay, sorry for going over time.